In this video, we're going to look at a bunch of common functions and the graphs of these functions. And we call these the parent graphs of these functions because it'll be the most basic forms of these functions, so it won't have any alterations to it. So let's go ahead and get started with one that we should have seen at some point in the form of y equals x, but this time we'll call f of x equals x because we're using the function notation now. So this is a straight line. With slope 1 and y-intercept 0. So if you remember the y equals mx plus b form of lines, this is the m on this would be 1 and the b would be 0. So we can change this line by altering the slope, altering the y-intercept. But in its most basic form, it is just f of x equals x. Right, so this is what we call the parent graph. So the graph of this one, if we just make it, I don't know why I wrote yx, an xy chart here, or an f of x chart if you prefer. I think we've already seen this in another video, but the points would look kind of like this. So just making a quick sketch of these, right? So you have the points 1, 1, 2, 2, etc. So this is going to be a straight line at a perfect 45-degree angle to the origin. So the domain of this graph, there's no domain restrictions here, so it's going to be negative infinity to infinity. And the range of the graph, which we haven't looked at before, but now that we can actually see the graph, it's easier to find the range. The range is going to be all of the y values that the function touches, right? Remember, this is the x, this is the y. So in this case, it's also going to be negative infinity to infinity. It's harder to find the range algebraically. It really relies on being familiar with the types of functions, which is why we're going through the basic types of functions that we'll come across here. So it's hard to do it algebraically, but with the graph, we can visually look at what y values the function is touching. So a special type of line, this is the most basic line, but in a way, we can have an even more basic type of line, which is f of x equals c, where c is a constant. Okay. So on the last line, we had f of x equals x. X was a variable. This is f of x equals c. So x is still defined as a variable because we're calling the function f of x. But x is nowhere on the right side of the equation, right? So c is just going to be a number. So for example, maybe this would be f of x equals 2 or f of x equals negative 1/3. It doesn't matter. It's just that it's just a number and it's not, there's no variable to be found here. So in this case, no matter what our x value is, okay, so if we made an xy chart here, and we made our x's here, our y value would be c, no matter what our x value is, right? So you can imagine c to be any number you want. I just want to keep it general here. So let's say that this is c right here. Then our function is going to look like this, right? It's just going to be a horizontal line right at this point. So again, our domain will be all real numbers because there's no restrictions here. So negative infinity to infinity. But our range is just going to be a single number. There's only one number that the y value hits, and that's c. So there's a few different ways you could write this. You could just write just c, maybe. Maybe if you want to keep it with the interval notation, you write it as c to c included on both sides, right? So the only value we're hitting is C, and the bracket as opposed to the parentheses means that it's included. Okay. Sometimes with singular points like this, we might write it as a set where we write the single number in braces, or if you just have a couple of numbers, maybe write them in braces, similar to how we were writing it for the ordered pairs. So either of these would be acceptable here. Next, we're going to look at the f of x equals the absolute value of x. So the absolute value function, what it does is it takes any number, it takes the input, the x value, and it makes it positive. So it doesn't change the number at all except for making it positive. So if the number is already positive, it doesn't do anything to it. And if it is negative, it gives you the corresponding positive number. So if we made a XY chart to see what this would look like, let's say 0, 1, 2, and let's do -1, -2, since we know the negatives will be important here. 0 is just going to be 0. 1 is just going to be 1, and 2 is just going to be 2, right? Because these are already positive numbers. So when we put them into the absolute value function, it just spits out a positive number. When we put -1 in, it's going to spit out +1, right? So the output will be +1. And then same idea with -2. So sometimes we like to think about the absolute value as the distance from 0. And we always think of distance being a positive number. So if you imagine on a number line at -2, you are 2 spots away from 0, right? So this is what our output is, 2. So if we make this graph, we can kind of see that on the positive side, this is going to look exactly like the line y equals x, right? But then on the negative side, it's going to be a little bit different, because now at -1, our output is 1. And at -2, our output is 2. So this one's going to look like this. Okay, leaving us with this V shape. So our domain here, again, is all real numbers. As long as there's no restrictions on the domain, like a denominator or a root or something like that, it's typically going to be all real numbers. But our range is a little bit different. We don't have any negative numbers as outputs, because this function always outputs positive numbers. So our range is going to be 0 to infinity, right? Including 0, because we do have the point 0, 0. So we hit the y value of 0, and then we go up to infinity. Okay, next we're going to look at another one that I believe we looked at in another video. F of x equals x squared. And we're going to study, a lot of these we're going to study more in depth in their own videos, like this one, for example, because there's a lot of special properties that go into these types of graphs. This is known as a quadratic. This is the most basic quadratic function. And its graph, the shape of the graph is known as a parabola. Okay. So just thinking again about what this function will do, it's similar to the absolute value function in that it's only going to output positive numbers, because when you square a negative number, you're multiplying it by itself, so you get a positive number. So if we put in 0, we'll get out 0. If we put in 1, we'll still get out 1, because 1 squared is 1. But then once we start putting in higher numbers, the outputs get larger more quickly, right? So when we put in 2, we'll get out 4. And then if we put in 3, we would get out 9. Okay. Now on the negative side, when we put in -1, we're going to get out 1, positive 1. And that's again because -1 times -1 equals positive 1. Let me carry the table over here. When we put in -2, we'll get out positive 4 for the same reason. And if we put in -3, we get out positive 9. So we can see what this graph looks like. It's going to somewhat resemble the absolute value graph in that it's only outputting positive numbers, but it's not going to be increasing linearly on both sides, right? It's not going to be a straight line. So we have 1, 1, and then we have 2, 4. And I'm not going to draw 3, 9 because that will, stretch the graph quite a bit. I'd have to make the y-axis a lot larger, but you can imagine it's somewhere like up here, right? It's going to be pretty large on the scale that we're working with. And then the other side, it's symmetric across the y-axis here, actually, right? The -2 goes up to 4, and then same with the -3 going up to 9, which again we can imagine is up there. So it's somewhat similar to the absolute value graph in that it's only outputting positive numbers and it's symmetric across the y-axis, but it's going to get larger much faster. So the domain is going to be -infinity to infinity, no restrictions there. And then because we're only outputting positive numbers, the range will be 0 to infinity. Okay, so just a few more here. And this is, of course, not going to be an exhaustive list. We're just looking at some of the most common types. But we'll add on more as we go. F of x cubed. Think about what this looks like. Again, I want to say we've seen this one before, but let's just write this out. So putting in 0, we get out 0. Putting in 1, we get out 1. Putting in 2 to the third power, that's 2 times 2 times 2. So we're going to get 8. So this is getting larger faster than the squared function. By the way, this is called a cubic function. Putting in -1, this is going to be -1 times -1 times -1. So the first two -1s give you +1, and then +1 times a -1 brings you back to the negatives. So these outputs are going to be negative. And then same idea with -2, that's going to be -8 for your output. So if we go to graph this, we have a point at 0, 0. A lot of these parent graphs have points at 0, 0. 1, 1, 2, 8. 4, 5, 6, 7, 8. Okay, not perfectly scaled, but good enough. 1, 2, 3, 4, 5, 6, 7, 8. So -1, 1. -2, 8. Okay, so it's going to look something like this. Okay. Now the domain for this one, still all real numbers. And the range is also going to be all real numbers in this case. We're outputting both positives and negatives. Okay, now we're going to look at what's called a rational function. Rational function. We're going to have a whole series of videos on just these kind of functions as well. I believe we did this one as a domain example. So let's look at what the graph would look like here. So right away we should be able to see that 0 is undefined. right? So that's an important property of this graph, is that we can't plug 0 into the graph. And that's the only problem point we're going to have. So our domain is going to be everything except for 0. Now let's look at some other points here, and I actually want to put in some fractions as test points here. So let's try like 1/2 and then 1 and 2, let's say, to start. So putting in 1, that's just going to be 1, right? 1 divided by 1. Putting in 2, that's going to be 1/2. Now if we put 1/2 into this function, we're going to get 1 divided by 1/2. So if you remember how to divide fractions, we do same, change, flip, right? So maybe you're used to seeing it like this, and you would keep the first number the same, change the division sign to a multiplication sign, and flip the second one. So in other words, we multiply by the reciprocal. So 1 times 2 over 1, which is just 2. So this is going to be 2. Okay. And the negative counterparts to these will be the same thing, except negative, right? So negative 1/2 will be negative 2. Negative 1 will be negative 1. And negative 2 will be negative 1/2. So we're still going to need to think about this one a little bit, which is namely what's happening when these numbers get large or when they get really close to 0. So we know we have the point 1, 1, 2, 1/2, and 1/2, 2. And then on the other side, same idea, right? Negative 1, negative 1, negative 2, 1/2, and 1/2, negative 2. Now let's just focus on the positive side, because this graph will, you can kind of reflect it diagonally to get the same shape to get to the rest of the graph. If we go to 3, this function will be 1/3. If we go to 4, it'll be 1/4. If we go up to 100, it'll be 1/100th. So it's going to keep getting very, very small, but it's never actually going to touch 0, right? There's no x input we can put into this function that will give us 0. There's nothing that we can do 1 divided by that number to give us 0. So this is a concept known as an asymptote, where, try to draw this a little bit better here, the function is going to get closer and closer to 0, but it's never actually going to touch 0. And that line we represent with a dashed line at the number that it's getting closer to. So we say this function is a horizontal asymptote. So we'll get into this more when we get into the rational functions a little bit more. This is just kind of a preview of when we look at those functions. So I'm still not satisfied with this drawing here. Let's go ahead and try one more time. So I'm gonna go like this. And then it's kind of the same idea as we get closer to 0. If you imagine if we put 1/3 into the function, we're going to get out 3. If we put in 1/4, we're going to get out 4. If we put in 1/100th, we're going to get out 100. So same idea. There's nothing we can put in that's going to give us y equals 0. But we're going to keep getting closer and closer to 0 over here. All right. So same idea. We represent this with a dashed line, and we call that a vertical asymptote. And then this one's going to look exactly the same, just kind of reflected from that one, right? So it's going to be a mirror image. So these functions, as you can kind of tell, are very specialized. So that's why we're going to spend a lot of time on just these functions. Okay, just a couple more here. Try to keep these videos shorter. I apologize for this one being a little long, but a lot of functions to cover. Don't want to break them up unnecessarily. So let's look at the square root function. Okay, oh, and by the way, we should look at the domain and range of this function, right? So the domain, as we said, this is going to be negative infinity to 0, union 0 to infinity. In other words, we're only not including 0 in there. And then the range is going to be actually the same thing in this case, right? Because we're not ever touching 0, but we are touching any other y value. Okay. So negative infinity 0, 0 to infinity for both of those. Okay, so the square root function, this one is also one that has a domain issue, which is that you can't put in any x values that are less than 0. Okay, you can put in 0 itself. So 0 gives us 0. 1 gives us 1. Square root of 1 is 1. Let's look at the perfect squares. The square root of 4 is 2. Square root of 9 is 3. Right, so we can kind of get an idea of the shape from these. So we have 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, 3. Okay, so this is going to be kind of curving downwards this way. Okay. So we can't put in any negative numbers into the function, and we also can't get out any negative numbers of this function. So our domain will be, it'll be including 0, because we can put 0 in to infinity. And our range will be the same thing in this case, 0 to infinity. So even though this is going up very slowly, going out far enough, it still will keep going towards infinity. Okay. And now, by the way, any even root function is going to look similar to this. So the 4th root function will look similar. The 6th root function will look similar to this. Same idea with the squared and the cube functions. Any even power function will look similar to the squared function. So the x to the 4th, x to the 6th. Any odd power function, I should say, will look similar to the x cubed function. So x to the 5th, x to the 7th, even x to the 1st, aka f of x equals x, looks somewhat similar to this in terms of its direction. So with that in mind, we looked at the even roots, so now let's look at the odd roots, and this will be the last one here. F of x equals the cube root of x. Okay. So we make our xy chart. X is 0, then y is 0. X is 1, then y is 1. And we want to look at perfect cubes. Cube root of 8 is 2, because as we saw before, the 2 cubed is 8. We can put negative numbers in here. So when we put in -1, we get out -1, because we can take the cube root of negative numbers fine. And same with any odd root. So the cube root of -8 is -2. So we'll go ahead, put this in here. We got 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 8, 2, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. So -1, 1, or just sorry, -1, -1, -8, -2. And We'll connect them and it'll look kind of like this. Okay, so it kind of looks similar to the cube function, just kind of rotated around. And there's a reason for that, which we will see later on. So the domain here, negative infinity to infinity. And the range, again, even though it doesn't really look like it, is going to be negative infinity to infinity, even though it's growing very slowly. So it kind of looks like it's getting almost flat. Still, given a large enough x input, you can get any y output. So these are a lot of the common functions that we'll look at. We'll of course have more than this that we'll add on later. But yeah, this is a good starting point for the different domain and ranges and parent graphs.